All right, so let's get cracking on. So welcome back, everybody. Good afternoon. Welcome back to the security stream. My name's Jamie Pease. I'm the chair of the security working group. Um, so this is our, I think, fourth session of the day. I did tell you at the beginning of the day we've got a lot of security sessions today, which is excellent. So we're on I think Sue and I feel we're on a bit of a marathon today, don't we, Sue? With all the session slots that we've got, which is great. So yeah, a very warm welcome, and it gives me great pleasure to introduce Raj. Now, Raj, tell me, I know you're presenting live from Prague, but is this your first time to GSE?
Yeah,
Or,
that's right. That's
oh,
right.
okay. Oh, well, a big warm welcome anyway from the GSE family.
Thank you.
So
Thank you.
you're very welcome. Don't forget, folks, this for the purpose of feedback. So Raj's session is 8p. We'll talk about that at the end, about the importance of submitting your feedback. And just a reminder, if you've got a backlog of feedback from the other sessions, don't forget to get those in. But without further ado, I'm going to hand over to our presenter, Raj, now. Over to you, sir, and welcome to GSE.
Thank you, Jamie. Thanks a lot. Hello, everyone. As Jamie was saying, my name is Apurv Raj in full, and I'm engineering manager in AIOps value stream in mainframe software division of Broadcom. I've been in the industry for almost 2 decades, and actually, luckily, I've seen the evolution of modern software engineering and problem solving since I've been part of these 2 decades, solving these part of this journey. So it has been great for me, actually, personally. And my primary experience is mainly in distributed tech stack. Even though I'm working in mainframe software division, uh, my expertise lies in distributed technologies. And the reason is that mainframe supports modern tech stack. Mainframe is quite modern and it supports modern tech stack. And we are building modern observability solution for mainframe domain, at least within my team. So far in my mainframe journey, what I've realized that particularly when it comes to product adoption, certificates become a major roadblock for us. Blocker in a sense that it slows the adoption down because I see customers stumble upon it. Getting these certificates provisioned, applying those certificates, renewing those certificates, this becomes quite cumbersome. Whereas if you look at the industry per se, overall software industry has moved quite far. Actually, it's moving with fast pace, given the fact that it has its own evolutionary pressure to be more advanced and secure uh, when it comes to security. So that led to me into this thinking that we really need to do something about this, particularly in mainframe domain. How we can educate our customers, our users more. And this is where I think I came up with this idea that this particular presentation, what I'm doing, maybe helpful. It may be a good start for you to get into the more details and try to understand it further. So I think that's how we are going to work with this. And interestingly, the idea is that I'm going to cover the entire evolution of security landscape from the evolution of HTTP protocol until the modern times of federated authentications and OIDC and so on and so forth. And the intent again here is not to go into detail because I will not be able to go into the details of all these technologies. Probably I'll emphasize on some of these like TLS. I'm going to spend little time on TLS because, as I said earlier, that certificates had been problem based upon my understanding and my experience. So I'm going to provide little more insight just to help you understand what is this certificate all about. It's not so difficult if you understand it, the philosophy behind it. And then I will spend little more time on the OpenID Connect. OpenID Connect is the modern way of authentication and authorization. So I'm going to spend a little more time there. Otherwise, we will just touch upon it so that we just see the journey overall and be able to understand, enjoy, and consume it successfully in once you have good understanding about it. With that said, let's move on. So let's start with this OSI model. OSI stands for Open Standards Interconnection Model of computer networking. And it's the backbone of networking. And you know that TCP/IP was the lingua franca of networking, but other OSI layers like application presentation, session, or network data link, uh, they kind of, in fact, and I will not even talk about network data link physical. I would say that TCP/IP and network access had been quite standardized, but the application layer composed of application presentation and session was kind of didn't get into any standard form. Uh, the enterprises developed the applications and developed these layers as per their convenience, and hence the application layer is something we are going to focus a lot, because that's the area where most of the things I was talking about, like TLS or TC, OIDC, or certificates apply. This is the area I'm going to focus a lot, and this is what I'm highlighting here. And second thing is that uh, since most of the modern enterprise applications are web-based, again, the HTTP-based protocols are again going to be the focus of this presentation. So, and I had another last thing, which is difference in depth. So if you can see each layer can be applied with certain differences, and actually should be applied with certain differences. TCP has its own defenses to be applied. IP layer has something called as IPsec. Probably you might be aware about that. Network access has got its own defenses. Application has got its own defenses, which is the focus of this conversation. And in particular, as I said earlier, the HTTP part of it, the web part of it. Okay, so since we spoke about HTTP, so let's understand how HTTP even itself evolved. So during the early days of computing, most applications were meant for desktop computers, and the general idea was that you use FTP or something sort of that or simple mail protocols to get those files locally so that you can see that and understand those files. But there was no concept of browsing, quote unquote, browsing per se, what we see today, where you can see the resource, see the content, and then at the same time be able to download that. And that's where Tim Berners-Lee, he was a scientist at CERN, European Council of Nuclear Research. He developed a telnet-friendly service to download research data, because he was a scientist. So he developed this to download the research data and results. And eventually, this particular thing evolved to become HTTP. Initially, HTTP was only meant for GET as a command, but later on, as we all know, most other commands were also got added to HTTP. Now, another important thing here is that along with HTTP, something developed also, which was HTML, so that we can link the text and images together and see the complete thing. The protocol during its initial days was very simple. Open the connection to the server, request the information you require, and close the connection. That's it. There was no concept of managing the state, and protocol was very simple, as I said earlier. So given the fact that HTTP was stateless, it was simple. But since with more adoption of HTTP, more web applications started getting built, it started becoming a little complex. And there was a need felt that client and server require additional directives in HTTP protocol to communicate with each other. Because the simple HTTP protocol was not sufficient enough to meet the needs. Uh, Similarly, the request for specific URL resource was not enough for some complex conversation which is happening between client and server back and forth. And here we really need to understand some of the building blocks of it, because these are the very important thing. I think these are very simple concept, but I'm just going to quickly refresh that. Then there's something called as header in HTTP, which is nothing but name value pairs separated by colon. Now, headers basically help you exchange information between server and client. So client server can send you some key value pairs to remember, and client can cache those key value pairs, and in subsequent conversation with server can also send these key value pairs. So this is what is called as header, and I'll show you a very simple example of that. Cookies, another example of header. Cookies are essentially headers with the key value pairs. And eventually, as I said earlier, in order to meet the complex need of client server in conversation, something else was devised with the help of cookies, that was session management, which also helped you in personalization and tracking of your session, etc., etc. Now you can see here in the screenshots to show you how client server message exchange happens with the headers. I've highlighted the headers, and again you can notice that they are primarily name value pairs separated by colon. In the second screenshot, and I'm using curl here, as you can see, and in the second screenshot, curl command. In the curl command, I'm using this cookie jar option to save the cookie in my local file. And so that I can see those cookies later, inspect those cookies. So when you see that when server sends the response, server is sending the response with the two set of set cookie directive. And set cookie is a cookie, but it's also a directive which tells client to cache the cookie values and send them back to server in the subsequent request. But there's an interesting thing. If you open this cookie file right now, you will find nothing. And the reason why you will find nothing, despite the fact that, as I said earlier, cookie jar and the file name it is supposed to save the cookie. The reason why you will not find it there in the cookie text file is that these cookie, what you see here in the screen, are marked as secure. That means these cookies are meant only for HTTPS communication exchange, and hence browser will not store that, or in curl will not store that. So that's very simple thing about header and cookie. Quick refresher. So and now you see the timelines also. HTTP evolved in 1989, and subsequently, as we 1990, 1993 it further evolved. Around the time of 93, 94, I think some experimentations were done because there was a need felt that some of the resources being served by HTTP needs to be protected also. I mean, not everything should be accessible by everyone. and some kind of challenge response mechanism has to be devised so that some of these resources can be protected, and only with only those who are authorized to see can see those or download those. This particular thing later on came to known as basic authentication. Okay, now let's again keep a look at the timeline above. In the time bar, you see in 1996, RFC 191945 was published, which described HTTP 1.0 specification. And in HTTP 1.0 specification, you also see basic authentication. So actually you can go to RFC 1945 and read it. RFC is a good source of information. If you want to get details about anything related to security, I highly recommend that you read RFCs. They give you very authentic information and precise information. So RFC 1945 described HTTP 1.0 and it's also described basic authentication. And the most interesting part was that if you read RFC 1945, it also highlighted that basic authentication was not secure because the username and passwords are passed over the network as clear text. And that means some work was already on behind the scene to make it secure. And actually, I didn't mention this on this slide here, but SSL, I'm not talking about TLS here. SSL was also published in 1996, the same time when HTTP 1.0 specifications came out. But later on, uh, in 2000 or so, TLS was published, TLS 1.0, which superseded over SSL. And it became, it became fundamental to secure the web communication or web communication over internet. And subsequently, HTTP 1.0, which was published in 1996, that also got evolved with the new version of HTTP, which is HTTP 1.1, which was also published in 1997. Now here, let me also highlight that some of these specifications, the dates I'm talking about, these are the dates when they first appeared. Subsequently, over the course of time, they themselves have evolved. For example, TLS, right now, the current version of TLS is 1.3. So it has traversed from TLS 1.0 to TLS 1.1 to 1.2 to 1.3. So these protocols and specifications have also evolved as time passed and they went through different tests. These specifications have been modified to make them more secure, and it has evolved. Similarly, HTTP versions have also evolved. For example, HTTP 1.1 is still being used, but we also have HTTP 1.2 and HTTP 1.3. Now, since we spoke about TLS, and I said that TLS was fundamental and is fundamental, to be precise. Let's understand this with a simple scenario. Assume Elise and Bob are talking over web, and some malicious actor, say someone, eavesdrop on the communication channel and start reading the message. Now I'm saying that when TLS is not there, it's a simple, plain conversation, clear text being exchanged over the communication channel, and someone can inject into this communication channel and see what is being exchanged. So this can affect the privacy of your message. Even further, uh, this malicious actor can also inject himself into the middle of this conversation and can even modify this conversation. So Alice might be sending some message, but this actor can modify this and send something else to Paul. And this is very simple example, just to help you understand how TLS helps you. But effectively, if you look at TLS helps you solve five fundamental problems. Those are confidentiality, authentication, integrity, non-repudiation, and non-replay. Confidentiality means only intended recipient can read the message. Message remains confidential. No one can read it except the intended recipient of it. Authentication means before the exchange happens, both receiver and sender can authenticate themselves and they know whom they are talking to. Integrity means the message cannot be tampered with. Non-repudiation means once a message is sent, it cannot be denied. It cannot be altered. It cannot be denied. And non-replay means you cannot replay the older message again back via the same channel. So that's non-replay. And these five things helps you secure your communication. And that's where TLS helps or plays such an important role. I'm again giving you a very simple example. Of course, we'll see, as I said earlier, we'll see TLS in little detail. But here the schematic diagram at the right-hand side shows you that how you can use your private key and public key to encrypt and decrypt the message exchange that is happening over web. So you use private key, someone else's private key, public key to encrypt the message. Public key is something which is available publicly. It's not protected. It's open for anyone to access. So you use someone else's public key to encrypt the message, and that person whose public key you use to encrypt the message can only decrypt it using his or her private key. So that is the beauty of TLS. So let's try to understand what is this public key, private key, and all these things, how this happens. Because as I said at the start of this conversation, that certificate has been something I've seen being the major roadblock. So this is where I'm just showing little more detail. So you can see here there are certain set of commands I'm showing on the screen, which helps you create the certificate. So the first command is all about creating the private key and the certificate signing request, which we call it as CSR. And as a result, you get the private key, which is server key.pem here. So let's understand what is server key.pem or private key first. So if you look at private key, actually you can open the private key in any text editor, and you see that private key will begin with begin private key and ends with end private key. And in between, you will see some alphanumeric text, which is a random number or random value. And that is what it is. A private key is a randomly generated value that meets certain cryptographic requirements. At the base of it, it's a secure random number, which is resistant to any cryptographic attack, or supposedly should be resistant to any cryptographic attacks. Let's go further. So this is where I'm saying that simple pictorial schematic. What is this private key? So private key is some random number with some additional parameters. I'm showing the private keys in red here. A means this private key belongs to Alice, for the sake of this presentation. A means LS. It can be anyone who is trying to get the public key, private key created. Now, server certificate, the CSR, the certificate signing request. If again, this is a simple text file, you can open that, you can see that again, it starts with begin certificate request and certificate request. And if you notice that CSR consists of a public key that corresponds to the private key, which you see here, here in red. So CSR contains a corresponding public key of it. And CSR also contains information that identifies the entity requesting this digital certificate. This includes things like common name, organization, which organizational unit or country and state you belong to, locality. The identity information here helps CA, the certificate authority, validate one's identity and ensure that the certificate is issued to the right or correct entity, legitimate entity. That is why this information is going to be useful. CSR also includes some additional attributes like subject alternative name, which allows certificate to be used for multiple domains. Again, that's very, very important thing. And the key usage, which helps you understand what this certificate is going to be used for. What is this certificate intended for? So once you have the CSR, you send this CSR to certificate authority, and then certificate authority issues you a couple of certificates. First, he will the certificate authority will share the CA's root certificate, which you see here. Now, what you do, now once you get the CA's root certificate, you import that into something called as, particularly in Java world, I'm saying, but you can correlate with anything. You can actually do that in mainframe scaling and so on and so forth. So you import that certificate, the root certificate. That's CA's root certificate. And if you see CA's root certificate, it includes its public key, that is CA's public key. And interestingly, this is a root certificate, which means it's a self-signed by CA. It's a self-signed certificate by CA. So generally in the CA's root certificate, the subject info and the issuer info remains similar. Validity talks about the validity period. Key usage talks about what this certificate again is intended for. And you see there's a red icon here, right here. Now this shows that this certificate is digitally signed using private key of CA. And similarly here in the CSR, when you create the CSR, I forgot to explain that. In the CSR also, you see there's a red icon, which means the CSR is also signed by the private key of Alice. So you see there's a color code here, and on this red icon, the A is written. That means it's digitally signed by the private key of Alice, which helps the certificate authority see the sanctity of this certificate. Certificate is valid because it's signed by the private key, and you have the public key, and they can use this private key and public key to make sure that the certificate is valid. And finally, as I said, when you send the CSR to certificate authority, you get the root CA's root certificate, and along with that, you also get signed certificate. And signed certificate again contains the public key of Alice, because this certificate is being issued to Alice. All right. So this includes a public key of Alice. And this also has got things like subject info, which again talks about entity to which this certificate is being issued, some basic constraints extension, which indicates whether the certificate is CA certificate or an entity certificate. In the case it's entity certificate, the basic constraint extension typically has CA flag set to false, indicating certificate cannot be used to sign any other certificate. And similarly, as I said earlier, it can have subject alternative name, key uses, and all other things. And again, this is digitally signed by CA's private key. And now again, you can see that here in the screen. The icon has got CA name. So again, this certificate is digitally signed. So, and again, once you have the signed certificate, you import this signed certificate into Keyring or Key Store and simply use that. And I've seen this step remains one of the stumbling block. So once you understand what this private key, public key, and CSR contains, I think this makes it little easy for you to manage these. Now, the final thing, at the extreme right-hand side, you see we have been using this term digital signature, digitally signed, or signed certificate. Oh, what does that mean? So I'm just giving you a very high-level idea about it. So whenever we say it's a digital, whenever we talk about digital signature, basically it's a hash of the content which is being digitally signed plus encryption applied on top of it. So you just create the hash and then you encrypt the hash. That is the digital signature. And when we say something is a signed certificate, that means it's a CSR, of course, because you sign the CSR. So CSR, basic CSR certificate signing request, plus the digital signature, which means the message hash of CSR plus the encryption. So this gives you an idea about whenever we say it's a signed certificate or digital signature, what does that mean? I'm not going to explain this in detail, but I'm just highlighting about this as to how this TLS works. In particular, MTLS. I'm highlighting MTLS because if you see later on in the slides, I'm also emphasizing that we should use MTLS in our applications. MTLS stands for mutual TLS. Generally, when we say TLS or TLS handshake happens, the owner slides with server to authenticate itself. The onus doesn't lie with client. Server says that I am the legitimate server. Client does not say anything about itself. So server says that I'm the legitimate server, here is my certificate. But in the case of MTLS, both authenticate to each other. It's not just server which authenticates, it's client also which shares its certificate and lets server understand that the client is a legitimate client who is supposed to use server's services. And this is very important. I think whenever you come across TLS, please make sure that you're using MTLS preferably. Now, you can read the details here, these steps are written, but fundamentally, the first part of this key exchange is all about asymmetric cryptography, which means the client and server come to an agreement to select a secret using which they will encrypt and decrypt certain messages. And they do that using this asymmetric cryptography. There are certain algorithms being used in TLS for this. RSA is one of them. Diffie-Hellman is very famous algorithm for key exchange. So that's also used. RSA is deprecated in 1.3, by the way, TLS 1.3. RSA is deprecated, and Diffie-Hellman is the recommended algorithm in TLS 1.3. And the second part is actually the symmetric encryption, where you actually encrypt the payload. So that's the second part. In between, you see there's a certificate request happening. So server sends the certificate request to client sends the certificate request to server, and they also make sure that they authenticate each other. So MTLS, working of MTLS is fundamental. Now we saw the previously in previous slide the need for basic authentication arose when we had some online resources needed protected access. So end user provided the credential. Um, these credentials can be some artifact to prove that user mapped to this credential, say username and password, should have access to this restricted resource. But user can have different credentials associated with the different resources. It can be email, it can be your banking portal, it can be workplace related resource, it can be anything. And for each of these resources, you can have different credentials. And another interesting thing is that for each these resources, you might be having different personas involved. Um, so a single user, so here the point I'm trying to highlight that a single user can have multiple personas depending upon the context, depending upon the transaction. And to identify this online persona, we use this term digital identity. The digital identity is nothing but the online persona of the user, which does not always uniquely identify the end user, which is a different problem, and we'll discuss about that later. And eventually, what happened with the advent of more online services, we saw this proliferation of digital identities, which led to uh, emergence of domains like identity management. So let's take a recap of what we have seen so far. Journey has been more interesting. Journey is going to be more interesting from here onwards. So let's take a quick look as to what we have seen. So we know that digital identity refers to and how what digital identity refers to and how with the advent of multiple online services, it became a real problem to manage these identities. And all these emphasize that the point here is that authentication is a complex problem, and it needs a specialized function to handle. It needs dedicated services to handle it carefully, to address the emerging use cases and the needs. So earlier solution, when we saw that digital identities started proliferating, and you used username password with the you started ending up with multiple username password for different sources. It led to the new business use cases to how to deal with these identities and these credentials associated with these identities. The earliest solution provided to manage this was known as or called as delegated authentication. It resolved the issue of managing multiple password because you can use same password to authenticate yourself for multiple services. As you can see here on the right hand side, that whenever you're trying to authenticate yourself against certain app, it simply forwards the credentials to this identity provider service, and the identity provider service validates the user and then sends the success or failure to the service, and depending upon that, access was granted. So it in a sense solved the problem of multiple username and password, but it has its own downsides. And one of the biggest downside was that you are sharing your username and password with someone else. So this identity provider may not manage the data, your username and password securely. What happens if there's a breach of data? Someone steals your username and password. That was the biggest challenge with delegated authentication. And second limitation it posed was the mm, was on the variety of authenticators that could be used in the case of delegated authentication. Because if this service, which is providing you this delegated authentication, changes the authenticator means how you authenticate. It can be, there's various ways you can authenticate someone. The basic, most common form is username and password, but it can be biometry, it can be OTP, it can be anything. So, so if service provider does not support the other authenticators, you're logged. You also cannot use other authenticators. So you're simply stuck with the basic form of username and credential as authenticator. So that was also one of the shortcomings there. The solution came in the form of federated authentication. So we are moving from delegated authentication to federated authentication. Um, and you can see here how it's solved. So assume and there's a user which is trying to access some HR portal within his organization. And what it does, the HR portal basically redirects user to the identity provider. You pass your username credentials to the identity provider. Identity provider issues a ticket, and you use that ticket to access your HR portal. HR portal validates that ticket to make sure the ticket is valid, and once that is done, access is granted. So this way, this ticketing mechanism is helping you validate it, and you're not sharing your username passwords, multiple username and passwords with identity providers. And the typical way, I think you can see that this particular phenomena, particularly if you look at your company. Let's say if you are working in some company and look at some of the major IDPs we have, identity providers we have. Okta is one example, Google is another, Microsoft is another. So if, let's assume Okta is your identity provider and your company name is my company, so you can have a basic login landing page, organization page, which could be mycompany.okta.com. And when you log in there, you will see different apps, and you can click on the app, one of the app, and you'd be able to access that. But in this particular scenario, what I'm showing here, I'm showing that first you go to HR portal. So let's say you have HR portal, HR app also, and HR app, you have bookmarked the URL of that HR app. So you click on that bookmark, then this bookmark will lead you to the IDP's login page where you log in. And then once you're authenticated, you're issued a ticket, and you go to HR portal with that token, and HR portal or HR app will validate that token and give the grant. So this is called as service provider initiated federated authentication, because the conversation is started from service provider. You clicked on the HR app first, and that's where it started. So this is called as service provider initiated federated authentication. Now, there's another variation of it, which is called as IDP initiated federated authentication. And here, as I said earlier, first you log into your IDP provider first. And once you logged in, you are issued a ticket, and you use that ticket to access other applications within your um, landing page. So you can have a number of apps or enterprise apps, and you can use that using that ticket. Okay, now let's track it back the timeline. In in our timeline where we stand right now. So if you look at it, Kerberos, or you may ask, what was when the federated authentication was created, or when it came into the picture? And the simplest example would be that Kerberos is a very sound example of federated authentication, which existed since 1988. I believe it was developed by MIT. But the challenge with Kerberos was that it was not web-oriented. It was complex. Similarly, Microsoft also introduced something called as NTLM, which coexisted with the Kerberos in 90s. But the challenge with NTLM was that it was not so secure. Even later on, it was deprecated, and Microsoft actually adopted Kerberos. But in early 2002, a new protocol was developed known as SAML, Security Assertion Markup Language. And it evolved quickly to become a web-based identity and privileges verification management protocol, allowing users to do single sign-on multiple domains. That happened in 2002. But eventually, as I said, with other standards like HTTP and TLS, SAML itself evolved. So 2002, it was first published. But further, it evolved with upgrades and enhancements to added to that. In 2003, SAML 1.1 came into the picture. In 2005, SAML 2.0 came into the picture. So here in this diagram, what I'm trying to show here is that SAML is quite a mature protocol right now. I'm showing a simple identity and access, high-level schematic of identity and access management system using SAML. And you can see there are several entities playing a role. The IDP interacts with the user store for user information and authenticates with authenticators of many kind, and SAML supports all these. User store could be a lab server, or it can be a cloud-based user store using some REST service. It can be anything. And your IDP can maintain SSO. SSO can be independent component. The service providers can start using tokens, and IAM solutions can provide these secure token services as part of this IAM solution. So there are so many things that can happen with SAML. So SAML, the crux of the matter is that SAML is a mature protocol and still widely used, particularly for legacy applications. Now again, why? Because it came into the existence around 2003. And 2005, we saw SAML 2.0 evolving. And that time was the time when XML was the lingua franca of web. XML was primarily used. And if you on the same time, during the same time, if you remember, SOAP was the protocol for web services. So SAML also supports SOAP. So probably that is the reason why SAML is still used, but for the legacy applications, which are still using SOAP-based web services and still using XML as the primary language there.
Raj, 10 minutes to go.
Oh, okay. Okay, then I think I need to quickly browse through the remaining slides. So during the decade of 2000, you can see the birth of many social media giants like Yahoo, Google, and Flickr, and you name it, you can see it here in the screen. And that led to a lot of new use cases. assume you had a freelance developer and you wanted to give him access to your organization's resources as long as he's working on your project, but you don't want to add him to your enterprise IAM directory services. How will you do that? Or another use case that you want your employees to access social media sites, but employees don't want to reveal all the information to the employer. So how do you do that? When I'm saying employers don't want to reveal, that means um, uh, the enterprise or employee is helping you log into these sites using enterprise account. So how do you take care of these things? So all these led to new and interesting use cases. And further, we saw that social media, some of these social media giants became very powerful with more people joining, and eventually they became themselves unto themselves identity provider. And that's where the traditional model of federated authentication, where service providers trusting identity provider and identity provider trusting service provider, because if you remember, service identity provider is issuing the ticket and service provider trust that ticket is valid. That kind of model uh, didn't fit well with social media platforms as IDP. And further development that happened was around content mashups and API-driven development. Now you have LinkedIn, you have Twitter, you have GitHub, and what do you want to do? You want to post your LinkedIn feeds to Twitter, or you want to post LinkedIn Twitter feeds to your Facebook wall. How are you going to do that? So you are creating content on some platform, consuming it on other multiple platforms. All this led to this content mashup scenario, which was kind of, it became difficult to address with the help of SAML. And that's where OAuth came into the picture in 2007, and eventually OAuth further developed into OAuth 2.0 in 2012. OAuth is fundamental. I think we are going into the final bylanes of security here. OAuth is fundamental because OAuth helps you solve that problem. How it helps you solve the problem? You see in this picture, I'm just giving you a high-level diagram as to how it helps. So, for example, you have some application which you want to use LinkedIn APIs so that you can post Twitter feeds or your LinkedIn post to Twitter feeds, for example. So first, what you do, you register your application in the LinkedIn developer portal, and by registering that, you get some client ID and client secret. Now you do, after doing some proper configuration at your app side, when you try to log in, basically your login gets redirected to LinkedIn authorization page where you authorize yourself, provides the access, authorize that, okay, on my behalf, you can use use these information. And once that authorization takes place, you get the authorization code. We further use that authorization code to get the access token. And now this client app, which is acting on your behalf, can use this access token to use LinkedIn API, which what we call it as the resource, the LinkedIn resource. So it can use LinkedIn APIs and can do things on your behalf. But the important point is that OAuth is not is an authorization protocol. Basically, it helps you delegate responsibilities, and that's what I'm trying to say, that in the case of here as a Hill statement, that the Hill statement is something called, what we say is who, what, wow. It describes who, what, and wow, which means I, the user, is who want to grant Twitter access to my Facebook wall, is what, to post my Twitter feeds is wow. So someone can do that automatically on my behalf. That's the wow factor. And OAuth helps you solve that authorization problem. And essentially, if you see, the access token is kind of valid key, which gives your application certain permissions to do things on users' behalf. But OAuth is certainly not the authentication. And this is the biggest mistake generally we tend to do. I think organizations have used OAuth as the pseudo authentication protocol, but that should not happen. That's not the case. That's not it's meant for. I will quickly move on. And this is where the OIDC came into the picture, the OpenID Connect. OpenID Connect basically evolved from OpenID, which was released in 2005. Then OpenID 2.0 came in 2007. And eventually OpenID was deprecated, and OpenID Connect was released, which was built on top of 2.0 as a base in 2014. OpenID Connect solved the problem of authorization as well as authentication. How? The same picture, what we were saying earlier in the case of OAuth 2.0. It's exactly the same pictures, exactly the same explanation here at the left-hand side, with some changes, and those changes are highlighted in bold. So when your app is sending the authorization request, redirecting you for the authorization request to the authorization server, LinkedIn authorization server, it adds a scope, additional scope as OpenID. That's the one change here. That is a small change it does. And what happens then, in addition to getting the access token, you also get the ID token. So access token is meant for your APIs to do some delegated things on your behalf with certain scope. And ID token helps you authenticate yourself. ID token is meant for authentication. Access token is meant for authorization. And this is how OIDC solves the problem. And generally, in the case of OIDC, client app, here in the client app and LinkedIn auth server, we say it as a relying party, RP, and OIDC provider. In OIDC parlance, they're called as relying party and OIDC provider, or OP. This is a very general scheme of OIDC. These are you can see different components of OpenID provider. You have a discovery document where you can see what are the different endpoints, what services are provided by OpenID provider. You have a token endpoint, you have a authorization endpoint. Token endpoint is primarily used when you get the token and you want to validate it, whether the token is valid token, you use that token endpoint. So you send the token to the token endpoint, and you get the response whether the token is a valid authenticated token or it's a false token, and so on and so forth. And this is what I was saying earlier. The discovery document basically gives you the metadata of what OpenID offers you. Now, one interesting thing, LinkedIn being shown as OpenID provider, but actually LinkedIn is not the OpenID certified, quote unquote, certified OpenID provider. But of course, these are uncertified implementations of, I will not even say uncertified implementation of OpenID. I would say they are using OpenID Connect protocol to get the authorization and authentication problem solved. But if you want to adopt OIDC, the recommendation is that you go for the certified OIDC providers. Who are the certified OIDC providers? Okta is one of them, Microsoft, Google. There are many. You can go to openid.net/certifications, and there you can see who are the certified providers of OpenID Connect. Again, a very quick comparison of OAuth and OIDC. You can see how similar they are, and it again relates to the fact that OIDC is built on top of OAuth 2.0. So now you have OAuth and OIDC both have three-legged protocol. You have resource owner, authorization server, and resource server. Um, and similarly, in OIDC, you have resource owner and OIDC provider, which has got authorization server and user info server and different endpoints. So user info server is nothing but you get the ID token, you pass the ID token, and you get the user info from the user info server. So these are the different endpoints. You saw that in uh, this discovery document here. So finally, I think we're not left with time, but so far we have seen password as the main form of authentication along with certificates, TLS. But there are other factors of authentication. We are not going to discuss those, but high level NIST categorizes these into three parts. Something you know, like password is a simple example of that. Something you have, mobile device with OTP is one such example of something you have. FIDO is another, but again, FIDO stands for Fast Identity Online. We haven't got time to deal with that to discuss more about it, but FIDO is another thing. And third category is something you are, which is primarily about biometric characteristics of the person, iris, fingerprint, face. The crux is that we must use multi-factor authentication in modern times. A single factor authentication is not enough. That's the crux of my message here. Of course, some other time we can look into that. And then we have these foundational identities, which basically talks about identity proofing, how you make sure that these digital identities actually relates to a unique person. Post-quantum cryptography is all about making sure you're using right cryptographic algorithms with right key sizes so that they cannot be broken easily, of course. And that's why I'm using the term easily. And zero trust security is a new paradigm, which is also known as perimeterless security. And it says that never trust, always verify. It's an evolving paradigm. And one thing I would like to highlight here is that MTLS is fundamental in zero trust security, and we discussed MTLS. Probably that is the reason why I touched upon it. Wherever possible, we should use MTLS in our applications. And that is it. That is it.
Thank you, Raj, for that, for taking us through that. I'm sorry, everyone, we ran out of time for questions because we've got to get ready for the next session. So it's a bit of a conveyor belt today. So apologies, Raj, for not being the opportunity to do that. So yeah, this is session 8P. There's a QR code there. If you've got a smartphone, just take a photo of that, and that will use your camera, and that will take you to the feedback page. And of course, you can do it on the website as well. Thanks once again, Raj, for that. And I know your first time for GSE. Some interesting. I did have a couple of questions myself, but I'll save those for offline. But no worries. So yeah, we're back here at in 3 o'clock UK time. A session with Brian Childs from IBM. If you remember, Brian was with us yesterday. He's going to be talking about defending the APS methods, new and old. So one not to miss, but of course there are other sessions going on in the other streams. So join us if you can. Thanks, Raj, once again. Thank you, everybody.
Bye, Jimmy. Bye, everyone.
Thank you. Bye.